Look at what I want to show you today. I want to introduce you to some different kinds of numbers. I want to, your whole lives you've always dealt with what we call real numbers. And let's get all the phones and pockets there. All phones can be away from. There's a whole different system of numbers or set of numbers that's just as important that you've never even seen before. They're called imaginary numbers. I'm going to tell you right up front that's a horrible name for them. It somehow seems to imply that they are something less than real numbers and that they're weird and imaginary, and these other ones are so concrete and real. And that's not the truth. That's not the way it is. But we need these numbers. We need these numbers to do things like solve that equation, for example. We want to solve that equation.
Why is that so important?
Oh, it's important. Now, to solve that equation, to solve that equation, what would we do? What's first step?
Subtract 10.
Okay, subtract 10. Step number 1. Agreed. Step number 2. Divide by 3. Good, because we're isolating x, aren't we? Okay. Now what? Square root. Excellent. Uh-oh. What's the problem?
Make it a decimal.
Okay, but I'm going to have a hard time making that a decimal because there's something weird going on here. So I get the answers, x equals plus or minus the square root of negative 12. What's the problem?
It's a negative.
It's a negative number inside the square root. Okay, now we've always said in the past that you can't do that, right? In fact, we've always said that for real numbers there are 2 things you can't do. You can't divide by what number? What number can't you can't divide by 0, right? Can't divide by 0, and we can't take the square root of a negative number, right? And here we are trying to take the square root of a negative number. Okay, and is the answer it can't be done? Well, yes and no. It can't be done for real numbers, but it can be done for a different kind of number, called imaginary numbers. Okay? And that's why we introduce these things, so that we can solve equations like this. Because there is a solution. The solution that we're going to get out of solving this quadratic equation means something, and it can be used for important applications. Later on, if we have time, I'll show you, I'll give you an example of something that I just remember from college as being an amazing use of these imaginary numbers. It takes a real problem and it makes it much, much easier to do. And that's the goal, really, of physics and engineering, is to understand the way the world works mathematically, but oftentimes real numbers are not enough to do that. We need something else. Now we've got it. Okay, but this is new. How are we going to deal with this? Okay, well, first of all, we have to, as I've already kind of let the cat out of the bag, we have to enlist the use of these imaginary units. And the definition of the imaginary unit is, we call it I, and it's equal to the square root of negative 1. So in the past, we've always been told we can't take the square root of a negative number, and here we are doing it, but it's no longer a real number. It's an imaginary number, hence the I for imaginary. Okay, it's used to write the square root of a negative number. That's the only purpose, really, is to be able to take square roots of negative numbers. So, properties of these things. Okay, well, if r is some positive real number, could be pi, it could be 16, it could be 11, but it's positive, then wouldn't you agree that the square root of negative r, that's a situation where we've got a negative number inside the radical. If r is positive, multiplying it by negative 1 makes it negative, right? Agreed? Here's what we can always do. We can always split that apart into 2 parts, like we always have in the past. Right? In the past, we've always, well, when we've simplified, we haven't done very much of this, but at the end of second semester, when we simplified radicals, like say we simplified the square root of 50. How do we do that? Okay, what is the biggest perfect square factor of 50? 25. So we broke that apart into the square root of 25 times the square root of 2, right? And then we just said, well, the square root of 5, we can write more simply. What is that? 5 times the square root of 2, and that's our answer, right? That's a simpler version of the square root of 50, but to get there, we broke it apart into two pieces. We broke it into the square root of 25 times the square root of 2. We're going to do the very same type of thing with a square root of a negative number. We're going to break it up into the square root of negative r into the square root of positive r times the square root of negative 1. And the square root of negative 1 is different. That's this new thing we're talking about. That's I, the imaginary unit. And so this just becomes the square root of r times I. A lot of times we'll put the I in front of the radical though, so when you write it, you don't, like sometimes if I wrote it after the radical, I wouldn't know, is that I inside or outside the radical? It's really just a sloppiness issue. It's not, there's nothing mathematical about it, but we like to put the I in front of the radical so we know it's outside. We can't mistake it for being inside the radical. Does that make sense? Okay. So, this is what we're able to do then. Now let's look at some real examples of this. What if I had like the square root of negative 3 or the square root of negative 4 then? How could I write those in terms of the imaginary unit? What would I break the first one up into?
Square root of 3 and square root of 5.
Square root of 3 and the square root of negative 1, which is I. Right? So what's the answer going to be to the first one?
I. Square root.
Yeah, I times the square root of 3. Make sense? Okay. Second one.
I times the square root.
And what's the square root of 4? 2. So what's the answer?
I times 2.
Yeah. I times the square root of 4, which we'd write as 2 times I. Just like we put a variable after the integer, we put the I after the 2. The reason we put it before the square root, once again, is just because we don't want to confuse it as being inside the radical. Okay? Is the I a variable? No. It's a number. It's a constant. Just like pi is, it's a constant, only it's a weird one. It's not a real constant. It's an imaginary constant. Okay. All right, so some properties of, if we look at powers of I. I'm going to do this without the PowerPoint here for a second first. So I to the 1, anything to the 1 is just itself, isn't it? Right? What's I squared going to be? Anybody have a suggestion?
I times 5.
Okay, it is I times I. That's true. Okay, but what happens if I is the square root of negative 1? What happens when I square a square root? Oh, okay, and you're right. Answer that question for me though. What happens when you square a square root? Okay, it cancels the square root out. So if I square the square root of negative 1, I should really just eliminate the radical and get a negative 1 left over, right? So I squared equals negative 1. Make sense?
So I squared equals I.
So I squared equals negative 1.
But not I.
Not I. I is the square root of negative 1. It's different. Okay? Yes. Why wouldn't it be? But it's not. It's the square root of negative 1 squared. Right?
Yes.
Okay? Does that make sense? And when you square a square root, you're just undoing the radical. Okay? Make sense?
Yep.
Okay? All right, so what about I cubed?
Negative 1.
Negative 1 squared.
Okay, now, I'll give you a little hint here. Is there a way, do you think, that you could come up with a tricky way of saying I cubed in terms of stuff that we already know? We know I to the 1 is I, and I squared is negative 1. Okay, why don't you get out your notebooks? You're going to have to write a couple things down. If you don't have your notebooks, I'll give you a piece of scratch paper. I'm going to have you just jot down a couple. You know, these. Hand that back, please.
Me.
Okay, Okay, so what do you think? Suggestions. Could I write I cubed in terms of I to the 1 and I squared? It's not, it's close, it's not I. It's negative I. How'd you get that?
Because it's, well, I cubed is the same as I squared times I.
Yeah, does that make sense? I cubed is the very same thing as I squared times I, right?
Sure.
That works, doesn't it? Because when we multiply like bases, we add the exponents. You've told me that many times in the past. So my base here would be I. I to the 2 times I to the 1 is I to the 2 plus 1. That's I cubed.
What even is going on?
Okay, so now this looks weird because they're i's, but if I had said what's x squared times x, you would have told me what? X cubed. Because x to the 2 times x to the 1 is x to the 2 plus 1, right?
What's that?
Right? Does that make sense? Okay, and once again, the reason for that is when we multiply like bases, we add the exponents, right? So why did we do that? Well, what is I squared? Negative 1. So I cubed is equal to negative 1 times I to the 1 is just I. What's negative 1 times I? Negative I, right? Negative 1 times anything is just negative that. Negative 1 times 4 is just negative 4, right? Negative 1 times x is just negative x, right? So I cubed is just negative I. And probably you were trying to make something more profound out of that. No, that's it. That's all I'm looking for. I cubed is the same thing as negative 1 times I, so negative I. Okay, what about I to the 4th? Can you think of a tricky way of coming up with a value for I to the 4th? There's a bunch of ways we could do it. What's an easy way? Okay, we could do I to the 3rd times I. That's fine. What else could we do?
Wouldn't it be positive 1?
Yes, it is. How'd you get that?
Because there's like a pattern.
There is a pattern. You're right. This is all about a pattern. Okay, we could do, and that's, Jody suggested I cubed times I. That's fine. That would give me negative I times I. That's going to work.
Just I.
But it might even be easier just to do,
I cubed.
it might be easier to do I squared times I squared. Which is really just the same thing as I squared squared.
So is that the
So what's I squared?
I squared.
What's I
Oh my
squared
God.
by itself?
I.
Negative 1.
It's I.
Squared, what's negative 1 squared? So,
We've gone too deep.
okay, so I to the 4th always equals 1. Now it gets easy, right? Now it gets really easy because if I do I to the 5th, isn't I to the 5th going to be the same thing as I to the 4th times I? And what's I to the 4th?
1.
1, right? Does that make sense? So, from this point on, we're just going to follow this pattern. The next 4 are really easy.
1.
I to the 5th equals I to the 4th times I. I to the 4th is 1. So that's I. I to the 6th equals I to the 4th, which is 1, times I squared. But I know what I squared is. It's negative 1.
Yeah.
So I get negative 1. Right?
So just
I to the 7th equals I to the 4th times I cubed. I to the 4th is 1, but I know what I cubed is. I already did it. It's negative I. Right? I to the 8th equals I to the 4th times I to the 4th. 1 times 1. Right?
So I.
Okay. What would be I to the 9th?
I.
I.
So it
Wouldn't
just
it?
follows a pattern.
follows the pattern.
You don't really have to know all that other stuff.
Exactly. I to the, no, you're exactly right. We want to utilize this pattern. I to the 9th is the same thing as I, because it's I to the 8th, which is 1, times I, right?
Sure.
Okay, so I'm going to challenge you here. I double dog dare you. See if you can tell me what is I to the 27th.
What in the heck?
That's too easy.
No, it's not.
What?
Wait, what is it?
What's I to the 127th?
Negative I.
Yes, it is.
It is? Yeah. Yeah, because 7 goes, wait. No, I'm so confused.
Okay, Noah already got it. He got it right. He knew why he got it. He just confused himself, but he knew for a flash. He knew why it was negative I. How did he know so quickly?
It's a multiple of
3
3.
goes into it.
What do you mean? You're right, but what do you mean? Articulate that a little more clearly.
I3 goes into I27, so like, I don't know how to explain it.
Okay,
But 3 goes into 27 9 times, so 3 goes into 100, like 34 times.
okay, you're really close. You're almost very close to nailing it down. You're slightly off. Does anybody else want to just take that idea and tweak it a little bit? It's a great idea. It's almost what we're going to do. How could we come up with that being negative I? And I think what Noah did, you tell me if I'm wrong, is you said, okay, I know I to the 127th has got to be the same as I cubed.
No, I just, 7 was the on the end, so I put it.
Oh. Oh, I got you. Okay. Well, maybe he didn't get it so quickly. I was giving him more credit than he deserved on that one. So what is the trick, though? Anybody know? Now, didn't we say, would you agree that this cycle of powers of I just goes in 4s? Right? Every 4 I started over again, right?
Yeah.
Okay, we knew that, for example, I to the 9th was the same as I to the 1 because I to the 9th was the first power of I in a new cycle of 4. Does that make sense?
Sure.
Okay? How did we know that? Well, how many times does 4 go into 9?
3. Or, no.
2. I don't care about that it goes in 2 times. What I really care about is that how many are left over when 4 does divide into 9? 1. Does that make sense? Okay, so if I want to find out what a higher power of I is, I just have to ask myself, okay, when I break this up into cycles of 4, how many are going to be left at the end? In other words, 4 divides into 9 with what remainder? 1. I don't even care how many times it goes into 9. Well, 4 divides into 127 with what remainder? In other words, what's the next number below 127 that 4 divides into evenly?
3.
Wait.
3 is the answer. That's the remainder. Answer my other question though. What's the smallest number? 124, right? The smallest number that's less than or equal to 127. That's a multiple of 4. Is 124, right? So I to the 124th is what?
106.
1, right? Right? Because you get that? Because I to the 1, because 4 divides evenly into 124. And so that would mean that it's at the bottom of one of these cycles, all right? Think about these numbers. 4, 8, the next one would be 12, right? The next one would be 16. The next one would be I to the 20 if I kept going. They're just even multiples of 4, agreed? So let me say that again. The largest number that is a multiple of 4 that's less than or equal to 127 is 124. So that leaves how many left over? 3, right? Because 127 minus 124 is 3. So I'm going to go down to the bottom of a cycle with I to the 124, and then I go to the top, I to the 125, 126, 127. And the third step down in any cycle is negative I. So we can write that in maybe a little simpler way. Here's our strategy. And this isn't a huge deal. It's not like we do this a whole lot right now. But eventually we'll do more of this. Or you will. Okay, we saw this pattern. if we want to do higher powers of I for larger exponents, all you do is divide the exponent by 4 and then use the remainder of that quotient as the exponent instead. So I to the 127th, we could trade for I cubed. They're the same answer. Okay? Divide the exponent by 4 and use the remainder instead. Much smaller number. And then all you have to know are the first 4 powers of I. And that's it. Okay? And if you know the definition of I, those first 4 are pretty easy to get. Okay, make sense? Okay, so what's I to the 23? Don't say it out loud. Everybody try that on your scratch paper. I to the 23. Okay. What's I to the 23? Don't say it out loud. Just point to it on your paper. You got an answer. There you go. Oh, no. Three, yeah. That's it? That's what you got? Okay. Three's the remainder, so what's IQ? That's it, right? Okay, so, yeah, I think people are starting to get this. So we know that 4 goes into 23 5 times, which we don't care about, with the remainder of 3 that we do care about. So therefore, it's going to be the same thing as I cubed, which is negative I. Okay? Alrighty. So, probably a little more important is, how do we do arithmetic with these strange numbers? Okay, so, what about something like that? What if we want to do the one on the left? We want to do quantity I times the square root of 3 squared. What do you think? Think about that for a second. What could I do? I'm going to give you a little hint. You're going to give yourself a little hint, actually. If I want you to multiply out these 3 numbers, what is the product of 2 times 3 times 4? 24. How did you get that?
I multiplied the 2 and 3 together and then I multiplied by 4.
Okay, so one way to do that would be to say 2 times 3 times 4. What's another way?
2.
Okay, I could do, so I could do 2 times 4. Is that what you meant? Is that what you said?
3 times 4.
Oh, 3 times 4 times 2. Good. So we could also make it 3 times 4 times 2. Right? Those are all the same thing. We multiply things in pairs, and we can associate the pairs any way we want to. Remember, we said that multiplication is commutative and associative. We can mix the factors in any order we want to, and we can multiply them in any groups of pairs, any groups of 2 that we want to, right? So a more convenient way to do this one then might be something like this. How about? Well, you tell me. I times the square root of 3 quantity squared really means what? If I square something, what am I doing? multiplying it by itself. So really what I've got then is all the stuff inside the parentheses is being multiplied by itself. So I've got I times the square root of 3 times I times the square root of 3. What if we group those a little bit differently? Yes, ma'am?
I got I squared times 3.
That's it, right? If I group this differently, you can do I times the square root of 3 times the square root of 3, right? And that's the same thing as saying I squared times the square root of 3 squared. There's actually a property of exponents there that we'll talk more about later that you may or may not be familiar with from the past. If I have a product like A times B to the power M, do you know what I can do with that? Anybody remember?
A times n plus b times m.
But you probably meant A to the M times B to the M, I'm guessing?
Yeah.
Okay, that's right. So you can effectively kind of distribute that exponent to a product, but you can't do that if I'm adding them. And that's why, for now, that's not too hard to comprehend, and you've probably seen that before, but we'll spend a lot more time with that later. You gotta be careful. A lot of times people wanna do this also. They wanna write that as A to the M plus B to the M, and that is not true, right? You can only do it for products, okay? So we could use that property if we wanted to, or we could even just split these things up like we did and multiply them in pairs. The result is the same. We end up with I squared times the square root of 3 squared. Okay, now, what is I squared? What is I squared again? -1. Okay, so that equals -1. And then square root of 3 squared is 3. So my answer is -3, right? Make sense? Okay. Okay, so there's number 1. What about number 2? We started this earlier. You told me to subtract 10 and divide by 3 and square root, and we got stuck here. Now we can maybe finish this off though. So what is my answer going to be? I'm going to get a plus or minus what? Yeah. Okay, good. We know that when we have a square root of a negative number, we'll make it the square root of the positive number times I, right? Square root of 12, I can simplify a little bit. What's a perfect square that divides into 12? 4. So I can make it the square root of 4 times the square root of 3. Square root of 4 is what?
2.
Right? That makes sense? Yes, ma'am. Yes, you may. Okay, you might be asking yourself, well, tell you what, we'll hold that thought for a second. Okay. Yeah, never mind. Okay, questions? Okay. Okay, give me, real quick, give me kind of a, so far, I'm going to just do a little check here. Just kind of covertly, you don't have to broadcast if you don't want to, but give me a thumbs up for good, sideways for, okay, I'm sort of getting this, but I need, or a thumbs down, meaning what?
Nick Levy, come to the office, please.
Those are loud, aren't they? Okay, so, okay, that's good. I just need to get the pulse here a little bit. Okay. Okay, I will say this. I will say that I think that part of the issue is with complex numbers, or with imaginary numbers, sorry, is that they're just so weird that they kind of are, people just sort of shut down a little bit because they're thinking, my gosh, what is it, imaginary numbers, what are we, okay, don't fall into that trap. They're really not a big deal, and I'm going to show you something here that'll be helpful to you. That this will maybe eliminate some anxiety. A lot of what we're going to do with these things is just do arithmetic with them. It's really easy. Complex numbers is the set of all possible numbers. Now, we've only dealt with a part of that set you guys have your whole lives. You've only dealt with what we call real numbers. Real numbers are just a subset of the larger set of complex numbers. Okay, I'll go back to it. So here's the set of complex numbers. This is all you've ever dealt with are real numbers. There's this whole other separate set called imaginary numbers, and that we're talking about now, when we combine those together, we get the set of complex numbers. Okay? So that's kind of how you think about this. These two separate sets that make up this larger set of complex numbers. So a complex number then is a number that has a real part and an imaginary part. Okay, the standard form for a complex number is this: a plus b times I, where a and b are just real numbers. They could be decimals, they could be square roots, they could be fractions, could be any conceivable real number. But the important thing is that the first term does not have an I multiplied by it. So the first term is what we call the real part. The second term is what we call the imaginary part. Now, your whole mathematical careers to this point, you have dealt with complex numbers that only had real parts. They didn't have any i's associated with them. So for all of those numbers, the value of b was 0. Okay? Make sense? Okay, now that's changed. Now we're dealing with complex numbers where the i's are starting to show up. Okay? We could have both an a and a b in our numbers where they might be all real or all imaginary. But typically, they're a little bit of both. They have an imaginary part and a real part. So an example would be something like this. 5 plus 4i would be an example of a complex number. What's the real part of that? 5. What's the imaginary part? 4i. Okay. Okay. What's the value of a in this number? 5. What's the value of b? Sorry. 4. Not 4i, just 4, right? b is the coefficient of I. Okay? So, how do we represent these things? Okay, well, we can represent these things in a way that maybe is a little bit, gives them a little bit more meaning, gives them a value that we can compare to a quantity by putting them in something called the complex plane. So here's the complex plane. Not a big deal. It looks just like the XY coordinate plane, but the horizontal axis, instead of being the x-axis, we call it the real axis. The vertical axis, instead of representing y, we call it the imaginary axis. And so if we want to do something like, let's take 4 complex numbers, and let's plot these numbers on the complex plane. Where do you suppose this one is going to get put, that top one? What do you think the coordinates will be in the complex plane?
All boys planning to play tennis need to meet today right after school in room 106. All boys tennis players meeting today 106
What do you
right
think?
after school.
Okay,
Nick
good.
Levy, come to the office.
Okay, it's going to be a -2, +5. You're right. It's going to be right there. Okay. Where is the next one going to be? 2, 2.
Oh, hey.
Okay, it's going to be right there. Next one's going to be over 4 down 3, right?
Do this for the rest of the year.
You think so?
Go back to the cup. It's easy.
Next one is back 4 and down 3. Okay, so we're done here. But for today, I want you to just notice something. Which of those numbers seems to be the closest to the origin? That guy does, right?
Sure.
So we would say then in a sense, that is the smallest of the complex numbers that we've graphed. Okay, we'll kind of fill in the last few blanks tomorrow, and then you guys go work on this stuff.
There's lots of points.
Oh.